Hello. I'm going to try and do some more formalizing of monodic theory, uh, and more specifically, try to develop a way to do equivalence within within the theory itself, and what I was calling to show two different kinds: a standard equivalence, and then like a what I was calling a Tau equivalence, which is essentially that kind of equivalence between different ways of describing or representing monodes and neighborhoods. Um, Whereas the equivalence is just different, the different between different monodes or different neighborhoods, and it'll become apparent as I go on explain. I'm going to introduce a new operator called Epsilon, and it acts like a a special binding that allows a the illustrator allows the an equivalence to form if there isn't an equivalence there. And that'll make sense too as I illustrate it. So I'll get right to it. So I'll make a simple example at first, and then kind of go from there. So using epsilon, and each monode is going to have its own individual index. So this right here is the equivalence binding, the special binding, and it's binding these monodes in a way only if they are equivalent. That meaning, and with monodes, equivalency would only be the adicity. If the adicity is the same, it would be an equivalent monode. So essentially, it would say that mi if so I'll just just so I don't have to write it up there, because I could put a mi1 mh1. I just kind of wanted to use it as an example. And this is that standard equivalency I was telling you about. This isn't a Tau equivalency, just a standard one. So if these two have, and in this sense, we're just stating outright, we're asserting that the adicity of both monodes is the same. And since that's the case, then these two monodes are equivalent. So this is your equivalency between those two. And it can go for many things. Now, if something isn't equivalent, and I'll show that element 2. Let's just say, for lack of a better, let's just say that they're not. Those values do not equal. Say 1's 1 and 1's 2. It means they're not equivalent. So the resultant is that standard move. It just kind of absorbs it all back in. It doesn't really do nothing. It has a process, but the process leads to nothing because there is no equivalency there. And that's really the basic idea of equivalency using the epsilon operator. Anyways. And then the Tau equivalency, I haven't quite figured out a way to formulate it, just to basically demonstrate it. And that was essentially the one that was like, where we had, say, this neighborhood right here with those two monodes, and it's a neighborhood because they're bound. And we were seeing that it was equivalent to something along the lines of this. That's where the Tau is. It's kind of like a, I don't know, maybe a type equivalency. Just it made sense. So this is just shown between two different models of the same information or representations or however you want to call it. You have an equivalency between the two. And you've seen this before. Well, I haven't shown the tau part of it, but you've seen it before that it has that equivalency to it. Well, I feel like having an equivalency was a necessary step. Because you gotta when you're comparing and contrasting things, you gotta show whether they're equal or not. And obviously, anything that goes into the Mu universe that gets reabsorbed, if you will, it doesn't have relevance at that point in time. So there's a way to show that they're not equal, they're not equivalent to that. That's the whole idea behind it. It's just kind of the beginning of this. I haven't explored it in depth, like many other things. It was more of a recent like aha moment, and I'm going to try to go a little bit further into it as I understand it more. I'd like to sometime in a video later on, I want to try to show the analogy between a monodic system and a set, and then go into some unique sets you can develop within using a monodic system, well, analogous to a set. And I talked a little bit about in a previous video too, and I'll go a little bit further into that. But that's really the idea behind it. And you can honestly say that, oh, well, this right here has that. You know, and I don't really care what direction things are or whatever of this thing right here. Like I'm doing, you know, kind of that idea too. And since we're actually showing that it's an arm, you could basically just say those are all 0 because they had to give up an arm. So you kind of have that idea. So that's the idea behind equivalency and epsilon, the epsilon operator. All right. Thank you.